Okay, so this is now 16.5. This was going to be now where we're really going to start getting into the rest of this review. Now what we're going to talk about is some of the newer stuff. We're going to look at what's called acid-base equilibrium. But first, before we do that, we're going to define the two different kinds of acids that we have. It's important, strong and weak. Now, remember from earlier in the other videos, we learned that strong acids completely dissociate. In fact, we don't even put a double arrow here, do we? We just leave one arrow. If I have 1 mole of HA, I will get 1 mole of hydronium ion. For weak acids, however, I have an equilibrium. So just like what we just did in the last unit, if I have 1 mole of HA, what do I have? Well, X and X. I have to figure that out based on another acid, another K, called Ka now, which is the acid dissociation constant. But let's go back here because what we're going to focus on first is understanding how to manage these strong acids. Okay, so we're going to do strong acids and bases first. And after we finish this video, you'll have a formative assessment and your topic worksheets to do to help you kind of reinforce some of this stuff. Okay, so remember, we're not going to use the double arrows because HNO3 is strong, and dissociates 100%, right? Now, if I had another acid, let's say I'm going to react this with water too, chloric acid, it also has 1 arrow, hydronium ion plus ClO3 minus. These are aqueous. Okay? Now, so what that means is when I'm trying to calculate concentrations, I can determine the pH or the concentration of my hydrogen ion just directly from the pH. So let's look at this. So first one, let's look at HCl plus water gives H3O plus Cl minus. Or I could write it as HCl and not put the water in, goes to H plus Cl minus. So if that makes you more comfortable, the concentration of this will give us the pH or the concentration of this. Either one, I can write them interchangeably. So that means if I have 0.5 moles of this, I'm going to get 0.5 moles of this. Same molar of this. If I have 0.5 molar here, I'm going to get 0.5 molar here. So if I want to know what the pH is, all I have to do is take the negative of the log of the hydrogen ion concentration, which is the negative log of 0.5. This is why it is so important to understand whether or not this is strong. Because if you did this for a weak acid, say hydrogen fluoride, or hydrofluoric acid, I should say, that's not going to give you the correct value. You need an equilibrium expression in order to find X, and et cetera, et cetera. But I know this is strong, so I plug that into my calculator, and I get 0.30. I can do that on and on and on. 2.12, 5.47, and this one is 7.82. Now, in this case, we do get a number. What's happened here? I've shifted this from being an acid to a base, and that is actually not the correct pH, right? 7.82 cannot be correct. You cannot, because if you look here, I'm diluting, I'm making the concentration smaller and smaller. So as I dilute my strong, look what's happening to my pH. My pH is going up to neutrality. which could be expected, but because I have less H plus in there, right? So that's going to be a higher pH. Remember, the lower this is, the higher pH. The more of this I have, the lower the pH. We've got to remember that inverse relationship. So what will happen now is that you cannot go over 7 for a pH. You basically have gone to pure water, right? So in this case, what you would do is you would say that this pH is really 7. Remember, this is a measure. This is not a measurement. This is a calculation. If I measured it, it would measure at about 7. All right. Let's do the same now. If I have the pH, I can also calculate the concentration of the acid. So in this case, I'm taking HNO3O minus, going to H plus and NO3 minus. So if I have 5 moles of this, I have 5 moles of this because it's a 1-to-1 relationship. So all I have to do here, the concentration of H plus, HNO3, the concentration of HNO3 is going to be the negative, that's not right. So let's start over with that. The concentration of HNO3 for this one is going to be 10 to, we're going to do the inverse log, negative 0.72. Okay. When I do that and I plug that in, I get 0.19 molar. So let's put that in the calculator because I want us to get used to doing that. Second log negative 0.72 equals, and there it is, 0.19. All right. And if I keep doing that over and over again, you're going to see that as my pH goes up, my acid concentration that is causing that is going down. And that is exactly what's happening. So this is a perfect example. Low pH, very high concentration of nitric acid. High pH, very low concentration. And that kind of gives you an indication of how these strong acids and bases work. Okay, so let's look a little bit at strong bases as well. Strong bases are the same way. Now, if we look at Arrhenius bases, let's look at what our strong bases are. These are usually hydroxide compounds of the alkali metals, such as sodium hydroxide and potassium hydroxide, so the group 1. Other strong bases include compounds of alkaline earth, such as calcium hydroxide, strontium hydroxide, and barium hydroxide. All right. Now, for the same reason, let's draw this up here. I'm going to make a solution of sodium hydroxide. I'm going to draw one arrow. Caught myself there. Because these are strong, I'm only going in one direction. So if I have 1 mole of this, I have 1 mole of this. So that means that if I have 0.25 molar of sodium hydroxide, I have 0.25 molar of hydroxide. If I take the negative log of this, right? So I'm going to put this here and put this here, the negative log of 0.25 is equal to 0.60. Now that I have this, I can take 14 minus this, and that will get me 13.4. Similarly here, this is a much lower concentration of hydroxide. So again, I'm going to have a much lower concentration, if I have a low concentration of potassium hydroxide, I'm going to have a low concentration of the hydroxide ion, as would be expected. If I plug that into and I take the negative log of this, I'm going to get a higher pH. higher pOH. But when I plug that in here, watch what's happening to my POH. As I decrease the concentration of the OH here, my pH is going to go down, because every time I decrease the concentration of OH, I'm increasing the concentration of H+. All right, now this one's going to be slightly different, because in this equation, we have to remember that for every one of these, I'm going to get 2 hydroxides. And just like we would in any other stoichiometric relationship, we have to account for that. So if I have 0.010 molar concentration of this, if I plug that in, or if I have 0.005 molar calcium hydroxide, I've got to have 2 times that in OH, because I get 2 moles every time. I plug that in my equation. The POH is 2 and my pH is 12. Okay, so let's just fill in some missing data here. This is the last little bit of the section. It says fill in the information on the tables below. Remember that something extra should be done to convert OH concentration for strontium because I have 2 of these, right? So what I'm going to do is I'm going to write these in for you. But this is homework. You need to see if you can do that. Here are the numbers for you to plug in. It's time to kind of get some practice. Again, you'll get a bunch of practice with this using your OWL. But we need to get really good at understanding how concentration and pH, how we calculate it with Strong's, because it's very straightforward. Because what we're doing is we're getting ready for our next section, which is a little bit more complicated and involves equilibria when we start looking at our weak acids.